Okay, so this is our session number 7, just after the midterm. Last session was mainly the midterm, and we finished the DC, module uh, number 5, I believe, for the DC machines. Today, we are going to continue the the modules, module number 7. We are going to start synchronous machines. Synchronous machines, as we said before, it's a relatively a large module, so we split it into 2 modules, module 7 and 8. Today, hopefully we will finish module number 7, chapter 5 in our book. Okay. Before we started the synchronous machines, as we finish each module, we solve one of the past exam problems. So today, let's solve one of the DC machines. I picked one, but yeah, you can, go through all the exams. You have all the exams in the past exams in our website. So feel free to start solving any problem for the DC or any other modules that we finished. So if there is no question, I'm going to solve this problem. It's a good one, actually. In December or the fall of 2016 exam, problem number 4. Yes, no questions. So I'm going to start solving this problem. And it's I picked this one to be honest because it covers many points actually and hints from the past exams. And this is how I pick or solve the problems. If you go through the past exams, you will find that the same, relatively, like the same idea are repeated every, like at least like every few years. So for this one is our DC shunt motor. Okay, let's start from the beginning. It's like a 30 horsepower. This power is, as long as you have a motor, this is the output power, P out. So for the motors, we defined the motors by their output power. Output power, it means like the mechanical power output of your motor. Your motor, so if you have a motor, you have input, it's electric motor, so it's electric. Output, it's mechanical. And of course, you have to have, this is like a motor, and you have to have the magnetic field, right? Or field or excitation, as we call it. Okay. So when you want to get a motor, usually it's defined by their output power, not the input. So this is the one is given. And the reason for that, usually your load, your mechanical load. So you want to like a certain motor that it can do or use to move, for example, your mechanical load. So you know your load, and you want to buy or get a motor to move or rotate this load. So usually the motor is defined by the output, or always, not usually, and the rated speed. What is speed? Here it's RPM. That's okay. The voltage of your electric supply, 240 volt. Once you see it's okay, it's a DC shunt, then the first thing is to draw the equivalent circuit of the shunt. So we start with the E first. You have one resistance here. We call it the armature. Okay. You have your, sometimes we call it the line or the supply. This is the, or the terminal. This is VT, positive and minus. And you have a shunt, RF. This is the resistance for the shunt. Sometimes this E, we call it like EA. Sometimes I call it E. Currents here, this is a motor. So the current is going in this direction. If it's the generator, it should be like in the opposite direction, but it's this direction. Then you have a field. Then you have the armature current. This is IA. This is I, sometimes we call it line. And this is IF. This is the first thing you do once you see in the exam, it's a DC shunt. Then let's complete the reading the problem. It's at rated conditions. Rated conditions, it means this machine is on this output power. The voltage is this voltage, and the speed is this is your speed, because it's working at the rated. And what is given here is the rated. They provided the efficiency. Okay, and as we said, the efficiencies for the machines usually between, let's say like 80 to maybe 90, or even sometimes 90 something. Let's say 95 or something percent. For the transformer, it's relatively higher, 98, 99 sometimes. So this is a good like value. What is the efficiency, or sometimes we call it eta? Eta is the output power over the input. So we have the output power and we have the efficiency. What power can we get? The input power. By the way, this is like in a percentage, so you have to multiply, for example, here 100. Or if you don't want to multiply by 100, you can put this one as 0.885. Okay. Then you can, from this equation, you can calculate the P input. The input power, the input actually electric power. Remember from this explanation? The input power for the DC, it's actually the power going to your motor, because it's DC, so it's the V terminal times the current. That's it. There is no cosine phi or like power factor, because it's DC. So this one is actually the V terminal times the I line. We have the V terminal, 240. You can calculate the line current. Okay. Okay. Then they said they provided some values here for the armature circuit resistance. So RA is given. RA is 0.096 ohm. Then the field resistance or circuit resistance, it's 93.6 ohm. So RF is given. And then they're asking you to calculate something like some a list of things. One note here is that the RA is usually much lower than the RF. The RF, because it's in shunt, it's much higher than the armature resistance. Okay, this is just to have like sense of the values that you see. You can see this one is almost 100. This one is almost 0.1. Okay. So how to, like, first point is to calculate the armature current, IA. So IA, to calculate the armature current, sometimes I put it like in a capital or small, it doesn't matter. Like there's just, you know, like it's the armature current, the current here. So to calculate this current, I already calculated IL, right? This current from this part. So I have IL. Can I calculate IF? Yes, IF is straightforward for the shunt. It's just the V terminal, which is the 240, over the RF, which is 93.6 ohm. So you can calculate IF. So you have IL, IF. Can I calculate IA? Yes. IA equals to the IL KCL at this point, at this node, IL minus, let me do it in this way. Yeah. IL minus IF. And then you can calculate the armature current. They asked about second one, about the output torque. By the way, I have the output power and I have the speed in RPM, but it's the speed. So what is the output torque? Torque out equals to the P out over omega. You have the output power, yes, it's 30 horsepower. You have to multiply by 746 to make it in watt. Omega is the rotation, or like the speed of rotation. It's N, the RPM, but you have to multiply by 2 pi over 60, because this one is in radian per second. This one must be in watt to get the torque in Newton meter. This is the output torque. The next is the mechanical developed power. Developed, or sometimes we call it converted. It means the power here at this level, at this brushes. Okay, you have the current and you multiply by the voltage. This is the power at this one. It's the power that is converted from electrical to mechanical. But still you have some losses. Okay. So the P mechanical develop equals to EA times IA, or IA capital or small, it doesn't matter. It's the armature. They asked to get the torque, developed torque, mechanical developed torque. So it's this power over omega. This is the torque developed torque, or converted torque, or induced torque, sometimes they call it. You know omega because we have already the speed in RPM times 2 pi over 60, and you can get the torque. The last one is interesting regarding like the starting or starting resistance, E. You have, they said the external resistance required in series are X, or are external, You put it here in series with the armature to limit the starting torque to 200. Remember, during the starting, sometimes we allow the current and the torque to go over its rated. But this is just for a short period of time. Okay, so 200% of the torque, remember the torque equals to the EIA over omega. So the torque is proportional with the IA. You want this one to be like 200% or 2 times. This one should be limited to 2 times. So 2 times IA equals to the VT minus E is 0, RA plus R external. This is the equation of the starting. Muhammad, you raised your hand. So do you have any?
Sorry, a question.
Yes,
Yeah,
yes, please.
regarding the mechanical developed power, I thought that the 30 horsepower is the P out.
It
Uh,
is the P out. It is the power here.
oh,
But in between, you have some losses. So the developed is just here. This is the developed power. But you still have some losses until you reach to the 30 horsepower. So what is the 30 horsepower? It's like the maximum, or it's not the maximum, the rated of your motor at its, like at the end of this shaft. However, in between, you have some losses, like you have, for example, losses from the air, like the resistance of the air. We call it windage. We have still core losses inside your, um, like your core, which is like the hysteresis and the eddy current. So you have the stray, of course, if it's there. So you have some losses between the developed and the output. So this is the output. Still, we have something called developed here. Sometimes we call it the induced, or like the converted. Sometimes we call it the converted. So what is the difference between the converted and the developed and the output? Some losses here in between. Losses, core, losses, hysteresis, and eddy. You have some, like windage, mechanical losses, friction, in between the developed and the output. Okay.
Thank you.
Yeah, thank you. And I can show you let me show it quickly, the one from the like the DC module. So from the DC module, I can try to open, not sure if it's here, but from the DC module, I'm not sure if you can see my screen. You only see the PDF, right?
Yes.
Okay, yeah, I can open, no problem. I can open the DC module. And because this is a very good question, you can, yes, from the DC module, let me clear this. So the power flow, this is the one that we need. Yes, it's here. So this is the input power from the motor. It's electric. As you can see, it's a V terminal times the line current. And then you have the converted or the developed here. And then you have some losses until you have the output. So you can see this one is smaller than this. Okay. Okay. Thank you. This is actually like a very good question. Let me go back to we have, yeah. Okay. Any other questions for this? I can try to repeat this one. So for this one is, do you want to have the torque during the starting equals to double of the torque of the rated, like the normal torque? So for this one, it means you can allow double of the armature current, which we already got. For the starting, it's V terminal minus 0 minus E over R external plus R armature. We have the R armature resistance. We already calculated IA, and you have VT as 240. You can calculate the external resistance that is going to limit your current and torque to 200% of the rated. If no question, now we solved the first part of this problem. Second one, They do something like changing the torque. If the torque in the load, they changed the load, they reduced the load to 40%. So we have the torque equals EAIA over omega. This one now 40% of what we already calculated. Okay. This is 40% of the one that we calculated. Okay. E is going to change, the I, A is going to change, and omega is going to change. So this is like three, you still have three unknowns in one equation. The idea for this one, and this is very common in the past exam, they change something, let's say the torque, by a certain percentage. So they're giving the torque, and you will have like different or three unknowns in this equation. So how can we solve this one? This will be our first equation. The second one is from the from the equivalent circuit. You have the RF and you have the RA, and this is the EA. You have one equation here. This is the IA. EA, small or capital, it doesn't matter. V terminal minus IARA. This is the second problem. Sorry, second equation. IA, we don't know it. V terminal, it's 240. RA, we know it. It's like this value. You still have two unknowns in this equation, the I, A, and E, A. We need a third equation to solve three unknowns in three equations. The third one is that E, as you remember from our session last time, E equals to K phi times omega. And we do the ratio. What is the first case? So we have two cases actually, 1 and 2. The first case is this one, is our original, this is the first case. The second case is our new part, or like the new section. We already calculated EA from the first part. K is constant, so it's the same. The flux is not going to change in the two cases. Why? Because you have the same V terminal. It's the V terminal across the RF, which is constant, so it's the same flux. The speed, you already have it from here, times, of course, don't forget, it's times 2 pi over 60. You can use RPM. It means you are going to calculate this one as RPM. But it's good to have it in omega, because you have in this equation, it's like radian per second omega. From this equation, you don't have the E2 and omega 2, which is here, like it's 2 here. You have three equations in three unknowns. You can calculate IA, the new IA. You can calculate omega, which is the speed. So the first requirement is to get the armature current. The second one is to get the speed. Usually when they asking for like speed, I recommend to have it in radian per second, and then you can multiply by 60 over 2 pi to get it in RPM. Both, like you can provide them like with the both answers. Last one is interesting. It's like different. It's to include external resistance in series with the armature to maintain the rated speed. So you want to add one resistance here, not for starting, but for something else. This resistance to keep the same omega from the case one, the rated speed, this one. Look, from this one, from this equation, from this ratio, we said we have the same K, we have the same phi, flux, like same flux, because the IF the same. If you have the same phi, the same speed, omega, it means E1 and E2 should be equal. I mean, but by that, like if you want to the same speed, it means you have the same E. Flux is constant, K is constant, so same speed, it means same EMF or E. Okay, same E, so you will get E from this case and use it V terminal minus IA, and then you will put external resistance plus the RA. And now you can calculate this external resistance. You have the armature resistance, you have the V terminal, and you have the E from this case, from case one, not case two, not the one you calculated here. No, the one from the, because you have the same speed. Then you can calculate the new or the external resistance to maintain the same speed. By the way, like why the speed is, or what happened to the speed? If you remember from the last session, it's omega and the torque. It's with the higher torque, what happened to the speed? It's lower. If you reduce the torque, as we said here, the speed is higher. So when you put some resistance, it's going to make like a kind of like electric load. So your speed will be reduced or return to the rated, let's say. It will return to the rated with the same like torque, right? So any question for this part? I can show you the quickly the solution for this one. We already discussed the solution, but I can show you like the, sorry, it's I guess it's this one. So this is this solution already uploaded in our website, so you can check it anytime under the past exam solution. So this is question number 4. Okay. First part, you draw the circuit, get the efficiency, it's output over input. Okay. You have to use the output as like watt to get the I and V in amperes and volt. Calculate the IL minus IF, which is IF is the of this voltage over the resistance, as you can see here. Then you have the armature resistance. This is what is needed at A, point A, or B, asking for the torque in the output. Okay. The developed torque, it's E times IA. Can you see the developed torque? You can compare this developed torque by the output. It should be like this one should be higher because you still have some losses. Then from the developed torque, you can calculate the, developed, sorry, power. You can develop you can calculate the torque, the developed. It's, look at this one, at this note, I said it's higher. Higher than what? Higher than the output. The output is here. You have some losses in between. Okay. Then you go to the starting, double of the torque or double of your starting current. You can calculate, this is the resistance, one something ohm, that's a good number. Then the next step, you change the load to 40, or you reduced your mechanical load to 0.4. Then you can use this value to have the three equations in three unknowns. 1, 2, and 3. Solve, you get the IA, you get the omega, or this is in the RPM. Okay. Can you see like the RPM compared to the rated? You reduce the load, so the speed is higher. To maintain the same speed, we are going to use the same E old, like E1, the first case. Then you can calculate the external resistance. And that's it. Like it's this is one of the full problems in the exam. Any question so far? Okay. If no question, we can start the module, our module number 7, which hopefully we are going to finish today, the synchronous machines. Okay, this is the beginning. We have to, as I said, we have two modules for the synchronous machines, module 7 and module 8. So this is, as I said, module 7, synchronous machines. We still have module 8. By the way, after we finish the synchronous machines, we only have one more module that is included in the PO exam, the induction machines, and that's it. So we don't have any extra things. Just to finish the synchronous, we have the induction, that's it. Next time we are going to do the module number 8, plus we are going to discuss assignment number 2. Assignment number 2 is already in our website. So for the synchronous, what we are going to cover, we are going to cover the main parts of the synchronous machines, explain the operation, and this one is important to understand the problems in the machines. For the parts, it's important mainly for the theory or like theoretical questions, or sometimes I call it like the knowledge questions. Okay. And then we will have the equivalent circuit similar to what we did with the DC machines, with the transformers. Okay. Then we have like open circuit tests and short circuit tests. They are not that important, similar to the transformer, but we are going to cover it. It's, I believe, very simple. You will see it at the end of this module. Next, in the next module, we are going to cover parallel operation of the synchronous machines and, you know, other interesting things for the synchronous machines. We have 3 main sections: operation and characteristic, then the armature reaction, equivalent circuit. Last section is the open circuit test and the short circuit test. Let's start without any delay, like the synchronous machines, as we discussed before. We will have these a couple of slides in each module, especially for the rotating machines. And the importance of this module, like this slide, is to show the difference or applications, let's say, for each machines. SM, the synchronous machine, their characteristic that they have a very large power ratings. Very large, I mean by very large, it's like in maybe hundreds of megawatt. Definitely you can find like a synchronous machine as maybe like 1 megawatt or even less. But one of the important um, characteristic that they can go to have extremely large values. So what kind of applications of this? For example, the pumps for the hydropower plant. So uh, all generation from the nuclear, from the natural gas, uh, from any kind of like generation in the grid, they are actually synchronous machines. Sometimes we use it even to move extremely large chips, steel mills. Like it was a very common application for the steel mills. So one characteristic of the synchronous machine is that they use what we call it a single speed. We call it synchronous speed. This is like the main thing. Something new that they started to have, variable speed drive. So you can change the speed of the synchronous machine. Actually, you can change the synchronous speed of the machine. You change the level of the frequency, so you can change the speed of the synchronous machine as input. Okay. Applications of the induction motors. We are going to our induction machines in general. We are going to discuss in the induction machine, say like module, but it's in general they are almost like the range of the power is very wide, as you can see, from kilowatt to megawatts, but few megawatts, not extremely large, similar to the synchronous. They are very popular in the air conditioners, for example, the elevators, the cranes, the electric vehicles, and also you can use the variable speed drive. And we discussed the DC machines applications in the DC, module, DC machine module, and mainly it's in the cars and some applications for the universal motors. Okay. This slide is important. It's including the equivalent circuit of the synchronous machine. Before we start, synchronous machine is AC kind, like the first kind of the AC machines. It's not DC machines as we just finished the DC machine module. This one is AC machine. AC, it means you will have, for example, 3 phases. You will have phase shift. You can have reactance. So not similar to for example, the power in the DC, it's volt or the voltage times the current. Here, there is a power factor. There is phasors or like a kind of vectors for mathematical, calculations. This one, it's similar to the DC machines, but with some, differences that I'm going to highlight now. This is a generator, okay, or motor, the synchronous machines. For the generator, it's a generator, so this is the direction for the current. If it's a motor, this is the direction of the current. You have armature resistance, similar to the DC machine. But you have something here called JXS. Now I cannot ignore this reactance. Now we will have reactance. S is for synchronous. So XS is the synchronous reactance. We have the EA, but the EA now is AC, not the DC. And there is no brushes. As you can see, there is no brushes here compared to the DC. The voltage here is AC. Like I can say, like it's a phasor. The current here is phasor. I mean by phasor magnitude and angle. Magnitude and angle. Okay. Phi here, the reason we put here phi, sometimes we use it for a phase, right? Phi, it means like phase. So phi, one phi, like it means like single phase. 3 phi, sometimes we use it. It means 3-phase system. So phi here, it means like per phase. This is AC machine, as we said. So this one is, all of this is per phase equivalent circuit, per phase. So if you, synchronous machines are always 3-phase, so you can solve this one per phase, and then if you need something, you have to multiply by 3, for example, the powers. And for the currents and voltages, make sure you, if you need to multiply by square root 3, for example. Okay. I said this machine is AC, but to be clear, this part of the machine, the armature, is AC. However, the excitation part, the field part, we use DC source here. This one is DC source. This is, we only use it only for the field or excitation. Okay? We are not using it for the AC part. The AC part, this is like AC machine. DC only, DC source here, only for the excitation. Okay. So this is the equivalent circuit. Because this one is DC and this part is AC, we are not going to do the similar to what we did with DC machines. We're not going to connect this, for example, in parallel, and we call it like shunt or something, or series, and we call it like series. No, it's always separated like this, similar to the separately excited one. Okay. Any question so far? Okay. Let's, yeah, we can discuss the next slide. And
Sorry,
I need,
question.
yes,
Then
please. Yes.
for the excitation part, so for the these machines, we should have two supplies, the AC and DC supply.
Yes. Yes. For the synchronous machines, you must have one source, DC source for your excitation. Yes, definitely. Yeah. And I'm going to explain this part because it's important. I'm going to explain it. Maybe I guess it's in the next slide, or yeah. No, it's like later. But for this slide, I'm going to discuss the torque, but later I'm going to discuss something, and it's important. I actually can try to discuss it now because it's important. What is the construction of the machine? The machine, you have stator. So you know the stator, the part of your machine that is not rotating. Okay, we have some slots here inside the stator, and we put the 3 phases. So you will have 3 phases here, A, B, and C. Usually, we put the field in the rotor. This is opposite than the DC machine. And this is the VF, which is the DC source. We have, for example, if you use your right-hand rule, so maybe like this is N and this is S, so you have a field here with this direction. At the stator, we put the armature. At the rotor, we put the excitation. So One reason for this is that, as I said, the synchronous machines are using for a very large ratings, and the windings for the three phases here are large. So you cannot put them in the rotor and rotate them. They are heavy, they are large, they are very big conductors. So to rotate them, similar to what we did for the DC, I just want to show you what we did for the DC. It was like, it's impossible. Okay. If you remember for the DC, we had like the stator. For the stator, we had the field. Okay. This is the field winding and terminals. And then we had rotor. Inside the rotor, we have the conductors, and then we have like the commutator. We connected the commutator brushes, and then we have our DC terminals. The armature was on the, or is in the, for the DC, is in the rotor. The field in the stator. So now what we did for the synchronous, we reversed this. We reversed the armature and the field. Like one time in the, like the lab, I found that they swap the armature and field in one of the stator machines. But this one was in just a lab, and it was like small ratings. So this one was not that heavy. So they said, okay, we can put it on, we can rotate them. But normally what I'm explaining here is the norm. Like this is the default. Okay. So armature in stator for the synchronous, field in the rotor. Do we need the DC source for the synchronous? Yes, always. How we do it? As I said, this is called the field, or sometimes we call it the excitation. You can check online, because this is a very interesting part, what kind of excitation and how can we provide the excitation of the synchronous by the DC source. You will find something like called brushless DC, synchronous um, machines, for example. It means the excitation, what they do, they have the synchronous machine and they put like a DC motor to provide the excitation by the DC source. We use, instead of DC machine, we use like AC machine, and we have rectifier. I mean by rectifier, power electronics diodes, and to inside the rotor source. Okay. And sometimes we put like the uh, rectifier, okay, using like thyristors to provide the DC source. Okay. So we have like different options that we can actually use to provide the DC source. Any questions so far? Okay, if no question, let me explain this one because it's important, and then uh, we can actually, because it's now it's a 7, we can have like a quick break, and then we can continue. Okay. So let me resume the recording. So for this one, we are going to derive the torque. So the torque in the synchronous machine is actually like maybe like due to like the resultant of the one from the rotor R and the one from the stator S. So the one from the rotor, as we said, the rotor, it includes the main flux. The one from the stator is actually the armature reaction. So the torque equals the K. Oh, K is a constant. At the end, it's like the flux density of the rotor cross product of the flux density of the stator. Okay. So like from this one, the cross product we already discussed before. If you have a cross product of B, so it's a B sine the angle between them. Let's say like sine delta. Okay. If A and B are at the same direction, so delta is the angle between them is 0, sine 0 is 0. If they are 90 degrees, sine 90 degree is 1. Okay. So for the like the one from the stator and the rotor, we have something called the net. The net is actually the summation of both of them, the one from the rotor plus the one from the stator. This is the net. So the one from the stator can be the net minus the rotor. You can actually use this one and substitute, sorry, with this here. So it will be like the resultant is the one from the rotor times the one from the net, and then cross product same one. So it will be 0. So at the end, it's similar to this. And this is actually the resultant torque. Resultant torque is the flux density of the rotor times the flux density of the net times sine delta between them. Okay, there is a reason we changed the stator to the flux density from the stator to the net for a reason. Okay, to use the angle delta. Angle delta is a very important one. It's we call it like the power angle, and we are going to discuss why this angle is important. So for this one, we have two cases. One is the generator for lagging power factor and the motor for leading power factor. Okay. The one from the generator, we have, this is similar to what we did with the transformer. So let's say we have the voltage as a reference, angle 0, as you can see. Horizontal, it means like it's angle 0, positive, and this is negative. Then you have a current, IA, with angles theta. Then we have this one perpendicular, you add JXS IA. By the way, we ignored RA, the armature resistance. Usually the armature resistance is very small compared to the XS. So most of the problems that we are going to ignore RA, but some few, like problems in the past exams, they include the RA. So it depends. If you have RA, you can use it. If not, then you can ignore it. This is because it's lagging. You can see the current. We added the current here, and then you have the E. Because V plus the voltage drop on the reactance equals to the E for the generator, lagging power factor. The flux from the armature is 90 degree from the current. This is the current, and this is 90 degree. This is the flux from the armature current. This is the from the stator. The flux from the original one, E, this is the original one from the field. The net is actually the summation, this plus this. If you move this vector here, it will be exactly the same, right? Same magnitude, same direction. We can do exactly the same with the motor, but here I used like a leading power factor. Okay. So it's E again, but now E is minus this to get the V. Okay. And you can see the E, 90 degrees, you have the B, this is the net, and this is the rotor. If you move this one here, you will have exactly the same, right? So resultant plus the stator, it will be the net again. And you can see the angle between them like the delta that we discussed before. So why angle delta is important? We call it the power angle. Delta. So delta, if you have two buses in the power systems in general, and this bus, you have a voltage V, angle 0, and this is E, angle delta. If delta is positive, then, or at least higher than the one here, it means the power flow, active power flow, will go from the one with higher angle to the one of the lower angle. If delta is negative, then, and this one is 0, so it means this one is the bigger, so you will have this direction. This is the reason you can find that delta in the motor is negative in the stator is, sorry, in the motor, and in the generator is positive. Delta in generator is positive, delta in the motor negative. Okay, it's important because we had one of the past exams about the synchronous motor, and the angle was in a negative sign. Most of the synchronous machines, I believe they are generators regarding the problems, but it depends. Sometimes very few times we had like motors. So with the motors, the angle delta is in negative. Okay. If no questions, we can jump to the next. So this one is, or this slide is important because in the exam, in the problems, you will see something like this. As we discussed in the DC machine, so they changed the torque to like 40% reduced or something from the original or the rated. Now, in the synchronous machine, you will find at a constant field current, and the load is changing, for example. So you will have something like this, similar to what we had from the DC machine. So before we start, we have this equation. We have a proof for this equation. Actually, in one of the past exams, they did ask about this, proof this equation. One of the theory or like the knowledge problems, they asked about this. I can show you like the, oh, sorry. I think it was here. Yeah, this one. This is the in the solution for the past exams number 4. Again, this one is in our website. So in spring 2014, they provided you with the same equation, and they asked it to prove it with the aid of a phasor diagram for the synchronous generator, of course. Okay. How can we prove this? First, we want to get the active power, okay, from the machine. It's a three-phase. So it's a 3 times the voltage in phasor, in phase, current in phase, cosine phi. This is the active power equation, okay, for the three-phase system. So we have this equation, okay. Let's use the phasor diagram for the synchronous. For the synchronous, you have, this is in AC, this is E, and we have X, S, J, of course. We have the V terminal, okay? And we have, we said this is generator, so we can have like the I like this, in this direction, okay? We can call it like the I armature or I or just I, that's fine. Sometimes this, we call it V terminal, or you can call it VP because it's AC, okay? So from this, as you can see, I did something here that I ignored the armature resistance. This is a valid assumption. So from this, you know, like the E, of course, it's in a phasor, equals to the V, okay, plus I JXS. For the phasor, you will have, this is the V as a, usually we take V as a reference, angle 0. Current, let's assume it's lagging, so you will have the current, and this angle is, sometimes you call it theta, sometimes phi, and the 90 degree, because of the J, 90 degree, you will have J, X, S, I, and then this is the E. This is the phasor diagram. And this one is delta. Why I'm using this? So from this, we have, this is E, and this angle is delta. Okay? Let's just try to explain something about if you have X and you have the angle phi. So this one, this area or this distance is X cosine phi from the trigonometric functions, and this one X sine phi. I did this because here we have E and delta, so I can call this part as E sine delta. Okay? From this right angle triangle here, the two angles here are equal because they are opposite angles, right? And this one is right angle. Here, this one is right angle too. So this angle will be phi or theta. Like it will be at equals to this angle. This angle equals to this. You can call it, let's say, theta or phi, whatever. So this one, this distance is J X S I cosine the angle theta. This one. By the way, this is equal to, as a distance, equals to this. So you can say this one is equal to the E sine delta. You can ignore the J because we are taking the distance, right? So from this equation, I can say I cosine phi or theta, I cosine phi or theta, whatever, equals to the E sine delta over XS. You can use this and substitute it here. you will find that it will be 3V E sine delta over XS. This is exactly what they needed. This proof was one of like a half question number B here for spring 2014. Okay, let me show you the proof in details if you don't have any question. So this is how we solve it. We assume that it's lagging power factor, ignore the RA. We included the phasor diagram. Can you see like the angles here are opposites or equal? Here is right angle. So this angle equals to this. Okay. Now this distance E sine delta equals to the IXS cosine phi. At the end, because we have this, now we can get the I cosine phi equals to E sine delta over XS. So the output power equals to 3VE sine delta over XS. Okay. And this is the, like the what is needed for the proof. And this is what we have actually in the synchronous machine as the output. One important assumption is we ignored the losses, the RA, at least the core, sorry, like the copper losses for the armature. Okay. Any question so far? Okay, no questions. So this is our equation. Now we understand this equation. So for this one, we are changing the load, not changing the, for this motor. This is a motor. How I knew that this is a motor? Because the angle delta is in negative. Okay. And this, for this equation, it doesn't matter. This equation is both motor and generator. In the motor, because you have negative delta, so the power will be, instead of like to the source, it will be in the opposite with a negative sign. Okay. So you can see something here interesting. It's you are changing the load. Okay, changing the load, it means you are changing the current. Even you can change the power factor of your load. You have different powers. Of course, the largest power is the number 4. This one is less, and until you reach to P1. Can you see that E is always constant? It's like on this circle. So the length for the E, the value for the E is always constant because the IF, the field, is constant, right? So the field or the flux is constant, then E is constant because E equals to K phi omega. If the flux is constant, of course, the speed is always constant, the synchronous speed, so E is constant on a circle here. I, like this area is I cosine phi. It's keep it changing, right? I cosine phi is keep it changing based on your load. This one is E sine delta. From this equation, always the voltage for the motor is constant. X for the motor is constant. So if you are changing the load, it means you are changing the power. It means you are changing this E sine delta or I cosine phi. Okay. I'm saying this because it's going to help us in the next one. So next one is like the one we are changing the flux, but the load is constant. the real power is constant. Because the real power is constant, can you see this is the I cosine the angle, theta or phi? Can you see this one is the E sine delta? It's constant. Voltage of your source is always constant. Okay. Any question? And this again is for a motor because the delta is in negative. Delta in negative, so motor, delta in positive, then generator. Okay. This part is neglecting the losses, so it means the armature resistance is 0. This is mainly the main one. And it's not just the resistance because we have other losses, core losses and other losses. So we assume that there is no losses just to make sure that the input equals to output equals to this one. Efficiency is 100% with this case, which is not realistic, or one, which is not realistic, but it's just for maybe like some to solve the problem or to do to get like approximated, not exact values, just for like overview of the problem. However, if you want to to do something like in details, definitely you have to add the resistance. Any question so far? No questions? So let's continue. Torque speed characteristic of the synchronous machine. We already discussed the one for the DC, if you remember, even for different DC machines. And we are going to cover it today with the synchronous and later for the induction machines. In the exams, for example, the one for the induction, I believe they asked for to draw a sketch for the torque speed characteristic for the induction machines. Okay, so sometimes they may ask for this. So for this one, what is the torque? The torque equals to the power over omega. So this is the power over omega. This is the torque, induced torque or developed torque. Okay, neglecting this equation, by using this equation, you neglect the RA. Because from the proof, we had RA equals to 0. What is the maximum value for the torque if the angle delta equals to 90 degree? This is we call it like the pull-out. Pull-out, it's like extremely large torque that you do not want to apply to your machine, your motor, or apply to your generator. So this is the pull-out torque. So this is the torque speed in N or omega, doesn't matter. You have rated speed here. Then after that, you have the pull-out torque or the maximum torque. We have one synchronous speed in the synchronous machines. Okay, this is a valid assumptions if your generator, let's say, is connected to the grid, to a very big one. We will discuss in the next module, what if we have two generators connected to each other? Not one generator to a big grid, but generator to generator. With this one, you will find that the speeds is not always the synchronous speed. I don't want to confuse you, but like this is just for the next, module. Here we have this case, generator connected to a grid. So speed is always synchronous. Whatever loading you have, you always have a same speed. Even we did hear something called the speed regulation. Remember the voltage regulation for the transformer? This one is similar. So you have the no load speed minus the full load speed over the full load speed. Okay, and this one is of course 0. Whatever you are loading or not, the speed is always constant. There is no regulation in the speed. Okay, there is no change in the speed. For this case, later we will see we may have in reality the speed is changing and we can adapt to this. Any questions so far? Okay. So this one is regarding the, like as you can see, the BH curve for the synchronous. It's similar to what we did with the DC machine. Okay, we have, like the saturation. When you have like a very large field current, you can reach to the saturation. Okay. And definitely, if you have the flux and the IF, you can transfer it to E and IF. Okay, and this one is E equal to K phi omega. This one, of course, like we have this equation before. The difference between this and the DC machine is, for the DC machines, we had the options to change the speed. So as I said before, you have multiple, or you can have multiple curves, and we called it family of curves. Here we only have one curve, just the synchronous. That's it. Okay. Usually, the machines operated at very close to the knee point. Not after, because it's a saturation, and not before. Almost at the edge. Okay. Okay. Let's get involved on the armature reaction, discuss more about the armature reaction. If you don't have any question, we can go to this section. The next section is related to the equivalent circuit, how to get the parameters, mainly RA and XS, or I can just say XS if we ignored the RA. Okay. No questions, so I can go to the next one. So for this, we are going to discuss now the armature reaction in the synchronous machines, which is actually something that is not like the DC machines. If you remember in the DC machines, what we said for the like the armature reactions or the AR, we said the armature reactions is something bad, and we need to get rid of this armature reactions. And we actually, you will see in assignment number 2, one of the theory problems that I included is I asked, okay, we have armature reactions. How can we reduce the impact of the armature reactions in the DC machines? But in the asynchronous machines, it's actually something inherently in the synchronous machines, and without it, the machine is not going to operate. So it's something really, really important. Okay, and it's already there. Like you don't have to add something to be there. So let's go with step by step to understand why the armature reaction in the synchronous machines now is important. So we assume that we have these machines. As we said, the field will be at the rotor. The phases A, B, and C, for example, here we said phase A, are at the stator. And this is the something normal for the DC, sorry, the synchronous machines. One thing that I can add here, can you see this one? This, we call it like the salient machine. Salient because you can see the pools. Sometimes, and in reality too, you can find that the rotor is something like as a circle, and we included the field winding in slots, similar to what we do for the stator. Okay. This one, we call it non-salient, or sometimes we call it like cylindrical. You cannot see the pools, but they have some pools here. Like, for example, they have N and they have S here and so on. Like here, you can see it. For the cylindrical, no, it's inside, but you cannot see or differentiate between where is the pools, for example. This one is salient, this one is non-salient or cylindrical. We have one theory question regarding this. Okay, so you have the field from the E from the field. This is the flux density from your field winding, and of course it's rotating with omega m. Okay. Then this is unloaded. Unloaded, it means you don't have any load. There is no current in the IA, IB, and the IC three phase. So then we are going to load this machine, and let's assume that it's like the lagging power factor, or lagging current, or lagging load. We have like angle between the E, the voltage, and the current. And the current, of course, is lagging. And this is the current. This is the E. Because of this current, you have a current, so you will have a flux, right? You have a current, then the resultant is flux. Flux is 90-degree away from the current. This one, okay, yeah, it's here. So this flux is due to this current, the I armature. Now you can get the resultants between the stator and the rotor. Okay. And this will be the net reluctance. Sorry, the net flux density, B net. So the one from the rotor, the one from the stator, and the net will give you like the voltage. Okay. What is the importance of this? So you have the voltage and you have the EMF here. There is something to add between them, and it's due to the armature and the armature action. Okay, this one we already defined that the net flux is flux density is the one for the rotor plus the one from the stator. Okay, so of course the one from the E from the stator is proportional with the armature. If there is no armature, you will not have armature action, right? So we can actually draw this one, like, sorry, we can write this equation as the voltage equals to E minus J X IA. By the way, the X here is not due to the inductor or the coil. This is something not real, but is due to the impact of the flux from the armature, or let's say the net, both. Okay. And for this reason, we call this one is like X of the A, like the armature reaction, for example. If there is no current in the armature, you will not have this X. Okay. Now we are going, so we have 1x due to the armature, 1x due to the armature reaction. We are going to add the one due to the coil itself. We call it the self-reactance. So this one is due to the armature action. Another one is due to the self-reluctance, the real reluctance of this coil. If you added both, you will have the synchronous reactance. One because of the armature action, one because of the self reactance of the coil itself. That this is the reason we don't call this one as the only XA, but it's actually plus the one from the armature reaction. So we call it the synchronous XS. It's the summation. Of course, both are in with J. Okay, we have armature resistance. As I said, most of the exams, they ignore the RA. Not 100%. Like I saw some of the exams, they still have the RA. Very small compared to the XS. So this one is much larger. Okay. Any questions so far? Okay. Let's continue. And you can see from this one that we have the equivalence circuit. Okay. For like the synchronous machine as different connections. For example, the star and delta, as we said, it's AC, it's a three-phase. For like the reason behind this is just I want to show you how we connect the equivalent circuit. All you have is the equivalent circuit for a single phase, but you can connect them, or based on your generator, you can have like a delta connection or star Y connection. Okay. And you can see here how can we connect them. Can you see like each one of them is like one of the circuits that you solve per phase. In the star or the Y connection, we have something called the neutral that we can connect to the ground, for example. Okay, or we can add a reactor here just to limit the fault current. Okay, especially for the asymmetrical kind of faults. Okay. Any questions so far? Okay, let's go next. I'm not sure, but you can see that in the synchronous machines, because it's AC, you can find some, yeah, I can say like similarity with transformers, right? For example, here, this is the phasor diagram for synchronous machines, or I can say synchronous generator, actually, because you add a V plus the I and times the impedance equals to the E. So different phasor diagrams for different operations. The first one is, of course, like the unity power factor, as you can see the current and the voltage lagging after that and leading. Okay. Then for all the cases, you can see that I, like this one and this are equal. It means I cosine the angle, let's say theta, and this one is E sine delta, are equal in all of them. It means they have the same power, the same active power. You don't change the power. You change the power factor, that's okay, but you don't change the power itself, the P. Same active power. Okay. but different power factor. For all of them are generator. Delta is positive for all of them. As you saw, like in the exam, sometimes they ask for the phasor diagram to draw like a sketch for um, the phasor diagram for a certain conditions, leading, lagging, or unity power factor. Okay. Let's take the open circuit test, the short circuit tests, to get the parameters of the synchronous generator. Mainly, it's a single parameter. It's XS. You can include RA, but it's mainly the synchronous reactance. So for the open circuit test, what we have is, let's have it here. You have your field winding, okay? And you are going to change this. Of course, it's a DC, and you are going to change this, or you can add the resistance here and change. Because it's open circuit, your machine is open circuit here. And you are going to have a voltmeter to measure the voltage here. Of course, there is no current here. Current is 0 because this one is open circuit. Even if you added like a voltmeter, it's almost open circuit, because as you may know, like the voltmeter has a very high resistance. As it's like open circuit, there is no large current flowing here, like very, very small current. Okay. So this one is open circuit. You change the field, you measure the field current with a meter here and get the voltage open circuit with a voltmeter here. So field current, measure the voltage open circuit. So you get some points here, right? Until you reach to the saturation. By the way, this one, the straight line, we call it like the air gap line. This is important to show you the beginning of the saturation and the knee point. One important thing is here is that we rotate this machine with the synchronous speed during this test. Okay. So this is the first test. You have what? Like the field current with the open or like, yeah, open circuit voltage, or E. We call this one the open circuit characteristic, or OCC. Sometimes we call it like this. The next one is the short circuit. So for the short circuit, what we do, similar to what we did actually for the open circuit, we are going to change the field, whatever by the DC or the resistance here. You have your synchronous machine, the armature. But with this, we are going to have a short circuit, or we can add a meter. As you may know that the ammeter has a very small resistance in the opposite of the, like the voltmeter. So in case you put your ammeter, it's as if you put like a short circuit. So this one, you are going to measure the current, but it's as if it's a short circuit. You are going to change the field, get the field, the current, okay? And calculate or get the measurement of the ammeter here for the armature. So you will have a plot for the field versus the armature and get the values until you reach to the rated value. Again, the speed is synchronous speed always. Voltage is 0. It's a short circuit here. Okay. This one, we call it the short circuit characteristic, SCC. Okay. So when you have both open circuit characteristic, short circuit characteristic, we can divide both of them to get the values for the impedance or the XS. So let's go back. This is the short circuit again. You can see the voltage here is 0. So E or this current is E over this impedance. This is what we have here. Then it's like if you want to get the magnitude, it's the E square root of R squared plus XS squared. And this is the impedance of the synchronous. It's the E over the IA. So you divide the E over the IA for the same at the same field. And of course, speed. Because XS is much larger than RA, so you can actually ignore the RA. So on the graph, we have the IF versus the E. Okay, this is the open circuit characteristic. We have the IF versus the armature resistance, and this is the short circuit characteristic. If you divide the open circuit test over the short circuit characteristic, or open circuit characteristic and short circuit characteristic, because this is a E and this is the IA. If you divide it at the same field, you will get something, and this is actually the XS. You can see the XS is here is straight line, and then with the saturation, it's decreasing. So this one, we call it like the unsaturated value, and this one is the saturated value for the XS. Okay, we ignored the RA, by the way, for this one. And this is only the XS. Okay. We have something like the short circuit ratio. This one, we measure the field current for the rated voltage at the open circuit with the field current for the rated armature at the short circuit to see what is the difference between both of them. For example, you can have a field current here and let's say like a field current, let's say here, for example. Sometimes they may align, so you have a short circuit of one, right? It's the same field current for both. Okay. Any questions so far, or? Okay, I believe we can have like a quick break and then return. So if you have any question for this module, or we can start, like discussing the midterm. Okay, no questions for this. We can actually go to the midterm. Sorry, I have to change the, okay. Yes. Okay, so for the midterm, we had a couple of questions. Maybe I can use with maybe full screen it will be. Okay, let me use it like this. So for the midterm, you had two questions. The first one is the magnetic circuit. Second one is the one of the power and the three phase and the wattmeter, the 2 wattmeter method. Okay. Let's start with the first one, the magnetic circuit, and I can give you like feedback. I already marked all the exams and sent you one email. The email is including the assignment one, so assignment one and the midterm. I added some notes, but if you want more explanation, like why, or you have any question for the midterm, we can definitely discuss anytime, maybe discuss during our session or offline through the emails. So feel free to contact me. Okay. So first problem is the magnetic circuit. I'm going to read the problem and give you like some hints from based on my experience on marking your midterm. So this is a magnetic circuit. The first step to do for the magnetic circuit is to draw the magnetic circuit. This is a magnetic circuit problem, right? So first thing is to draw the magnetic circuit, maybe just after you read the problem. So this one, for example, is a magnetic circuit given. They picked a certain kind of material because you have multiple from the pH curve, you have multiple of the materials. So they picked one, a certain one from the magnetization curve or the pH curve given. They have the depth of the core is, so because this one is 3D, right? So it's you have sometimes they call it like the depth or the thickness of your core is 75%. Okay. The dimensions is all the deltas, which is the delta 1, delta 2, is the distance in milli, of course, for the air gap. You have the W, okay, is here. You have the H. You have the L. This is the L. L is like all of these are the same L, right? All it's L. Coil 1, number of turns given 100. And given something about the flux 2 is 1 milliweber, this one. Asking to get two things. The first one is to get the flux 1. This is the one. The second is to calculate the current I1. This is I1 and Phi1. Okay. Let's go to see the pH curve. They said about it's a silicon iron 1%, so it's the one on the top. Ignore the cast steel and the cast iron. Ignore both of them. We are going to only use this one. The pH curve is given in B in Teslas and H in amps per meter. Okay, because sometimes they can change the like the units. Maybe like this one can be like in the field current, for example, and this one is the flux itself. Okay. So as I said, the first step to do is to draw the magnetic circuit, because from the midterm, some of you already tried to solve this problem without having a correct magnetic circuit. So magnetic circuit, how to draw the magnetic circuit? This one is coil, right? Coil, it means it's a source. Source, how can I put like the polarity, positive and negative, based on the right-hand rule? They already have the direction for the current, so it will be something like this. Use your right hand, put your fingers with, like the direction for the current. You will find that your thumb is the direction with the flux. They already have it here. So you know that this one is positive, this one is negative. This is the source. Then you will have reluctance for each part of your circuit. One is in the air gap, two air gaps for this one. You have your flux is split here and then this point. So you will have something like this, 3, right? With this one, I'm going to use one reluctance for the entire iron, like this iron. And one reluctance for the entire leg here. And another reluctance here for the entire iron here. As long as they have the same L as we have it here, okay, same thickness, same material. So you can use one reluctance for the entire part. Look at this one. This is the reluctance for the entire iron here. All of this. We can call this one as left, this one as middle, this one as the right, maybe like A, B, C, whatever you want. But how can I have it here? I will put one reluctance for the iron, one reluctance for the air gap, this and this. You can put them anywhere, like here, here, or you can put them like them here. It doesn't matter because they are in series, right? Then you will have one in the middle. You will have another one for the iron here. Last one is the one for the air gap. So this for the air gap, 2, this for the air gap 1, this one for the reluctance for the right, middle, left, and this one N times the current I1, right? This is the magnetic circuit, and you are going to get some marks for this one, like for just the magnetic, drawing the magnetic circuit. Okay. What is given? Like before we go, like what is given? This one is, we have a BH curve. Okay. So the magnetic circuit problems, all the problems, you check if you have for the iron part, do you have the BH curve or do you have the relative permeability for the iron? If you have the relative permeability for the iron, you are going to use the MMF for the iron equals to the flux times the reluctance. And you can calculate the reluctance because you have the mu R or the mu of the iron. If you have the mu R, you multiply by the mu naught, then you can get the mu of your iron or the ferromagnetic material. This is, we solved a couple of solved problem in the uh, sessions. It was like solved from the textbook, but this is not very common in the exam. What is common in the exam is that they provide the BH curve. How can we solve if we have the BH curve? I said this one is not common, but it maybe like for a couple of exams, past exams, they use this technique. Okay, I mean by not common, it's like not like the majority of the problems, but it may, you know, happen again. This is the reason I also solved problems of the textbook that they have the mu R. So what if they are provided the BH curve similar to this problem? If you have the BH curve, you are going to use the MMF for the iron part equals to the H times the L. L is the length, H is the, from the BH curve, the magnetic field intensity. Never use the phi times R for, all I'm talking now is about the iron part. For the air gap, we always use for the air gap V times R. The MMF for the air gap is always V times R. Why? Because we have the L over mu naught, which is given or known, times the area, and this is the flux. So for the air gap, this is the air only for the air gap. It's always like this. For the iron part, do you have the pH curve? So use this equation. Do you have the relative permeability and the or permeability of your iron? Use this one. Okay. The reason for that is the pH curve is include like many of the mu's because it's not linear. The relationship between the pH curve is B equals to the mu H, because mu is the slope between the pH curve. If it's a straight line, then it will be one mu, one slope, right? This is the slope. But the pH curve, no, they include multiple mu's, different slope. It's not linear, it's not a straight line. Okay. So now, if you understand this, we actually solved half of the problem. The next step is to solve the circuit analysis, similar to the circuit analysis. So you have the flux here, given the flux 2, it's given here, 1 milli Weber. Because you have this flux, and you can calculate the reluctance of the air gap. Remember, it's L, it's the delta, like the length, right? Over the mu naught, 4 pi times 10 to the power minus 7, A. One time I found in the solution that you got the A incorrect. What is the cross-section area here? So it's this times the thickness or the depth. This is this area. What is L here? L, okay, it's here like 50. What is the, sorry, seems, yeah. Sure, why, okay. So, seems, yeah, now it's correct. So L times, what is the thickness? It's given, or the depth, it's given as 75. So L times 75, or 50 millimeter times 75. This is the cross-section area for this air gap and this one too. So you have the reluctance and you have the flux. Can I get the MMF here? Or the voltage is similar to the voltage, right? The MMF here. Yes, it's the flux, as we said for the air gap, it's the flux times the reluctance. Then, can I get the MMF here? What is the MMF of this one? This is actually the one for the iron, for this part, this iron part. Okay, from this point to that point. All of this, not including the middle, okay? So to get this MMF here, it's, again, you have the pH curve, so it's H times the L. Can I get the H? Yes, if you have the B, because you have the pH curve. Do we have the B? Yes, because you have the flux. So if you have the flux divided by the area, you will get the B. From the pH curve, you can get the H. That's it. Another thing is to get the length. The length of this one, it's interesting because, you know, what is the length of this one? So it's this plus this plus half, because we are using the mean length, right? Plus this, like half of here, plus this, okay? Plus half here, and then half here, and then W, and half of the L. So this one is L over 2. Remember this L, it's L over 2. So this one is L over 2. This one is W. Sorry, sorry, H here. And then this one is W. This one is L over 2, L over 2. This part is L over 2. Okay, you can subtract this one, which is very, very small. It's like 2 millimeter. It's neglected. But if you want to like exact, yeah, it doesn't. It's not going to change your answer, by the way. So this is the H. Multiply H times L. You can get the MMF of the one on the right. We already got the MMF for the air gap, for delta 2. We got the one for the reluctance for the right. Now, because you have this MMF and this, you can get the one in the middle. Because doing like KVL here, this one on the middle equals to the one of the right plus the one of the air gap. So the MMF of the middle equals to the MMF of the R right plus the MMF of the air gap delta 2. And you can get this value. This value equals to the H times L of this one, the one in the middle. So you can get the H, sorry, the L over 2 plus the H plus L over 2. Okay. And you can calculate the H. Why I'm calculating the H here? H, you can call it M because it's in the middle, right? Why you are calculating HM? Because I will go again for the pH curve to get from, I have the H this time, so I can get the B. Why do you need the B? Because I can get the flux in the middle leg. Why do you need the flux? Because I have this flux already given, right? This flux is the one for the air gap. So I will add the one from the middle, then it will be the total, which is the one, like doing KCL here, which is the one or required, the first requirement. Okay. Now you have this flux. Can I multiply this flux by the reluctance of the air gap to get the MMF of the air gap? And then we can do the same H times L for the part of the iron. For the air gap, again, it's phi, the flux that we added the two of them, the resultant, or the phi1, times the reluctance of the air gap, which you can calculate L over mu R. L over mu R. Mu naught, of course. Sorry, mu A. L is the delta 1 area. All areas here are L, which is 50 times 75. Mu naught, 4 pi times 10 to the power minus 7. Okay, so you have the MMF of the air gap. Can I get the MMF for the iron part? Yes, it's H for the left leg times the L of the left leg. How can I get the H? By, you already have the flux, phi1 divided by area, you will get the B. From the BH curve, you can get the H. Having the H and the L, how can I get the L? So it's the length for this one. Okay, you have the H, you have the L, you can get the MMF. You have the MMF of the iron part. You have the MMF of this air gap. You have the MMF of the middle. Add the three of them to get the MMF of the source. At the end, the MMF of the source equals to, because it's a source, N times the current. You have the number of the turns, you can get the current I1, which is the one required here. Any questions so far? Okay, if no questions, I'm going to show you like the solution, which is I already uploaded, just to show you like the main trick actually for this problem. But the main, like the main or the important thing here is follow the steps for the magnetic circuit. The first thing is to draw the very clear magnetic circuit. Put everything you know, for example, make it big. You can make it bigger than this. V2, for example, is 1 milliweber. You have the reluctance of the right leg, middle, okay, left leg, and the air gap, 2, or sorry, 1. Here is 2, and the MMF of the source. I start with the air gap because it's straightforward. It's air gap 2. Phi times the reluctance, and then you can get this value. Okay. Then you have the flux for the air gap. You can divide it by the cross-section area to get the flux density. And from the air gap, you can get this value. Sorry, from the pH curve, you can get this value. Okay. Add the two, the iron and the air gap here to get the one in the middle. Okay, it's the summation. H times L. You have the H already, you have the length. Make sure you get the correct length. You can subtract this or you can ignore. It's not going to change anything. One important thing is that here I added something like approximate, because it's very difficult from the curve to get the same number as your, for example, your colleague. It's difficult. And even the marking of this question is something like approximate. I don't look at the numbers, but I look, they are close to my numbers. I don't look to the exact numbers. Because this is pH curve, I got it 100 just as approximate. But for you, you can get it like 120, 190, or 100 something, but it's close to 100, maybe like 50. It depends. Because if you look at the pH curve for 0.267, let's get the pH curve, and you will find that it's very difficult to get from the 0.26 something here to this. So it's something here. So it's almost, impossible to get the same number. This is one note, Then, after having the MMF of the middle leg, I'm going to get the HM, use the pH curve again to get something from like the pH curve, like the B, the flux density at the middle leg. Why I need the flux density at the middle leg? To get the flux of the middle leg and add it to the original one, or the one given, to get the flux in one. Okay, they all have the same area, by the way, so you can say flux density. Go to the pH curve. This is something interesting. We found that when I go using this value, it reached like it was outside the curve. It means you need extremely large H, you can add it as infinity. Okay, so the core will be saturated too, and it's impossible actually for this flux to flow inside your core. And for this reason, you can reach to the current, or you need like a current of infinity. Okay. Even I tried to show you here that there was, maybe I'm not sure, but it's maybe this problem they already uh, meant in the exam to have this, so they can see the note, or maybe it's a typo. But you can confirm that what like that the current is impossible to be a value and it's infinite by using just the flux from the two. Okay, and if you added this, you will again reach to extremely large value. Okay, so it's almost impossible to have this value. Any question regarding this one? If no question, we can, you know, solve or give you like some notes for the second problem. Second problem, it's first part, it's two parts. Okay. The first one is regarding the three phase. Second one is the 2 wattmeter method, the power. So let's solve one by one and see how we can proceed with this. Okay, so you have a load. The load is like a 20 kilowatt, 0.8 power factor. It's a three phase, of course, star connected load. So you have the total three phase power, the cosine theta, or the power factor. We can call it the power factor too. It's a three phase, of course, star connected. So it's good to know that it's star connected load. You can try to draw the circuit because, yeah, they are going to add more things here. For example, they said they are supplied by delta connected generator. So the generator is delta connected. Okay. And they are connected. Okay. So they are connected through feeders having a resistance of 1 ohm and inductive reactance of 1 ohm. So it's actually, you have a feeder. This is per phase, you have 1 ohm and J1, okay, plus J1. And you have another feeder here, so it's a three phase. So the feeder given is actually the one per phase. Always the feeders are given per phase. The line to line voltage is 230, line to line for the load, 230 volt. And then they ask it for something. Yeah. So to start this problem, as we said, we have to have any star to, sorry, any delta to star, and then connect the neutral to neutral and solve the per phase. So for this, I will have the load. I will have one of the feeders. It's 1 plus J1 ohm. Okay, this is your load. And then you will have the one from the star here, from the generator. The voltage actually for the load is 230 divided by square root 3, because now you are taking it as a phase, not line as given here. You can actually say, let's make this load as a reference, so angle 0. Okay. They asked about line-to-line voltage at the generator. So this is the phase, but then if you multiply by square root 3, you are going to get the line-to-line. Can I first calculate this V generator? Yes, if I have a current here and have this voltage, so this voltage plus current times the impedance, I will get the voltage at the generator. What is the current for the load? Can I calculate this? Yes, I have the power, which is 3 V phase, let's say, I phase cosine phi. The power is given 20. The voltage phase, or you can make like square root 3 and make it line. That's okay, because we already have the voltage line immediately, like 230. And then you get the current, and the power factor is given 0.8, lagging. So you can get this current as a magnitude. But this is AC. I need magnitude and angle. What is the angle of this current? This is lagging the load. So I will put negative sign, cosine inverse of 0.8, because I have the power factor. Why the current of the current has like a negative angle? Because we assume that the voltage is with angle 0. So if it's lagging, it will comes after, right? So lagging means it's negative sign, because I'm taking the voltage here as a reference. You calculated this current multiplied by this impedance, and then add this voltage, you will get this voltage magnitude and angle. The load current, we actually, to get the generator, we already calculated the load current magnitude and angle. They said something like generator power factor. Generator power factor is, you have this voltage, magnitude and angle. You have this current, which is the load current and the generator. It's the same current. They are both in series. So because it's the same current, you can take the cosine, the angle difference between them, the angle of the voltage minus the angle of the current. Okay. One thing is that I got this voltage of the generator phase. Okay. Phase. If you want to get the line, phase, I mean this is the voltage. If you want to get the line, you have to multiply by square root 3. Okay. Any question, because we finished the first part? Do you have any question? Okay. Let's complete like the second one, and then I'm going to show you like with all the answers. The second one is using the 2 wattmeter method. So from the 2 wattmeter method, if you remember, it's the V line, I, okay, I phases or line, and then cosine 30, and you put like plus minus. If it's a positive sequence, you add this. If it's negative, you add this, and that's it. By the way, the 2 wattmeter, like, or the wattmeters are, you have your loads, they are connected to the load, not including the feeders. Okay, because you want to get power at the load, not including the feeders. You have this voltage from the load, yes. You have the current, yes, we already calculated this current actually. You have the angle, if it's one will be positive, one will be with the negative sign, and you will get the wattmeter 1, wattmeter 2. As a check, as a like check, at the 2 wattmeters, they must be equal to the 3-phase power of the load. Any questions? If no questions, we can go through the solution. So this is, as you see, like I drew it like in a big way, so you can see the feeders, 1 plus J1 each, 230 volt line to line. This is the phases. I know that it's 20 kilowatt, 0.8 power factor, lagging. Okay. Per phase, you divide by square root 3. You added, or you assume that the phase A is the reference. Okay, you have the current of A. This is not like a real node, of course. And this is your generator side. You calculate the current magnitude and you put its angle with a negative sign because it's lagging. You calculate the voltage at the generator. And to get the line to line, you multiply by square root 3. You want to get the generator power factor, it's cosine the voltage angle minus the current angle. Okay, and of course it's lagging because of course the angle is positive, and you can see from here that the angle here is larger. This is positive and this is negative, so it's lagging power factor. The watt meters, you have two watt meters, voltage phase. You can of course use this one, the phasors, or you can use my method like 30 plus or minus the sequence that I included. Okay. You added the voltage here is 230 to 130 volt, the one from the load. The current that we calculated for the load, this current, 62. And then you cosine the angle. At the end, if you add both of them, they should be approximately equal to the 20 K. Sorry, like there is a typo here. So this one, 20 watt, okay, or 20,000 watt or 20 kilowatt. Of course, it should be obvious. Any question for the midterm or any part, like any question for any part of the course? Okay, by this, I believe we reach it to the end. I want to show you something regarding the module. So we reach it to, or we are aligned now with the outline. We finished now module 7 completely. Okay, and next time we are going to have two things actually. First, start with or continue the synchronous machine, having, as I said, um, mainly the parallel operation and the power flow again for the synchronous machines. Then we are going to discuss some questions similar to what we did with the assignment number 1. We are going to do it again with assignment number 2. Okay. If you have any problems that you want me to solve during the session, you can send it to me. And by this, we reach it to the end of this session. Do you have any question?
Sorry, Professor, question.
Yes, please.
Actually, they would be like, I think, 1 month and a half between when we finish this preparation course and the exam, the real
Exam.
exam.
Yes.
So meantime, I mean, we will have some times to go through all those questions because now we have on the weekends. Can we send like questions when we review all the past question to you? I mean, after finishing this course.
Yes, yes, definitely. You can send me anytime. Okay,
Oh,
even if you are not attending this exam, you are attending the one on the fall or December, that's completely fine. Also, like this is actually like good because you remind me with I asked at the school, you will have access to this course for 30 days after you finish fully and 60 days as observer. Observer, it means you cannot like send something, but you can see the contents. However, I highly recommend you to download the like the documents, the PDF and things as soon as possible. Like you don't wait until like the last day and then you will lose the access, but you can try. So because you still have some time between the course and the exam, the good thing that you are going to have access for fully 30 days and 60 days as observer.
great. Thank you.
So thank you. Thanks. I forgot to tell you about this last time, but yeah, it's good that I remember it now. Yeah. Thank you. Any more questions? Okay, if no questions, so thank you so much and yeah, have a good night.
Thank you so much, Professor.
Thank you.
Good night.
Good night.